Okay, let's practice with Faraday's law. Okay, so I'm going to write it in kind of the application form, which is delta V induced is equal to the negative time rate of change of the flux, which itself is B dot dA. Okay, where that integral is over the loop that we're considering. All right. Now, remember that truly what's a changing flux that's given by this integral is causing an induced electric field, but that can create a potential difference in space. And then if there's a physical wire there with charges, then it can drive current. Okay, so most often we are looking for I induced times R. Okay, V equals IR. All right, so that's most often what we're looking for. Okay, so let's try and see how we can apply this. We have to take care because Faraday's law deals with something that's changing in time and the possibility of something that's changing in space. Okay, so if the magnetic field's constant throughout a loop, then this integral just becomes a number. Okay, it may be changing in time, but this integral doesn't care about changes in time, just changes in space. And so we have to keep those two changes clearly separate. Okay, so I'm going to do an example where both of them are changing so we can see how to keep that separate. Suppose we have a long wire. Okay, there's a long straight wire and current is flowing in it. All right, so I'm going to say that's I wire. I'll subscript it IW from here on. And then near it we place a square loop of wire. Okay. That is a distance, let's call it R1 away, and its far edge is a distance R2 away. And this is of length L, length L. Okay, so it's a square loop. All right, now the thing I know is that I is changing, so di dt is equal to 100 amps per second. So 100 amps every second, which is a crazy lot amount of amps, but you can actually get this by doing 10 amps in 1/10 of a second, or even 1 amp in 100th of a second, which could happen in flipping a switch. Okay, so this is not an unreasonable change in current in time. Okay, so this would be like a current's changing at a rate of 100 amps per second, but mathematically that's the time derivative of I. Okay, so this is I wire again. So what we need to do is figure out, okay, in order to figure out the current flowing in this loop, we need to calculate the flux through that loop due to the applied field. Okay, now remember there are two different magnetic fields here. One is the applied field from this wire. This wire creates a field through this loop. Then this loop responds by Faraday's law and creates its own field to try and oppose that via Lenz's law, that minus sign. Okay, we're just going to focus on how to calculate a size. We've done some exercises that have already practiced with the negative sign. Okay, but I just want to focus on size. So we'll just do magnitudes to forget that minus sign. All right, so to do this, we need to recognize that the magnetic field from this wire, it's going up, and so the field is into the page. So B wire is into the page throughout this whole loop. But it's a function of distance. Okay, so when I'm trying to find I induced is equal to 1 over the resistance in this loop. This loop has some resistance R. And again, let's just do magnitude, so no Lenz's law minus sign. ddt of the integral over that loop, okay, of B field dot dA. Now thankfully B is into the page and that's perpendicular to the plane of the loop, which means it's also parallel to dA because dA points normal or perpendicular to the plane of the loop. So this just becomes B dA. Okay. But B is for a wire, which is a function of R. So this is going to equal 1 over R, B by dt, of mu naught I wire divided by 2 pi r. R is the distance from the wire to where we're measuring it, which means the field here is going to be R1, and the field over here is going to be R2, and it's going to change continuously. So that doesn't have a subscript, but I'm going to be integrating from R1 to R2. So that's the magnetic field, and I have to do dA. Well, dA is the integral of the area, but it's changing only a radial away from the wire. So I'm going to write that as 1 over R, d by dt, R1 to R2, mu naught I wire over 2 pi r, so that's all the same so far. Now dA is going to be technically some section here, but I could take actually a whole section of that area of that loop, which has a width of dr and a length of L. So that's the same thing as L dr. And so that dA became L dr. The whole length times a little dr. Okay, now this integral here only cares about changes in R. It doesn't care about things that are changing in time. Okay, I know this current is changing in time, but it's not changing in space. And so this integral doesn't care. The only thing that's changing in space here is that R right there. Everything else is a constant with respect to dr. So I can pull that all out. 1 over R d by dt of mu naught I wire L over 2 pi. And I'm left with R1, R2, dr over R. That's the only thing left inside that integral. Okay. All right, and that's not too bad of an integral. The result of that is the natural log. The integral of 1 over R is the natural log of R. So we can figure that out. So now let's focus our attention on this. This time derivative is acting on everything over here. So if R was changing in time, like if this loop somehow was getting bigger, okay, then that would be complicated. I won't do anything like that. But thankfully, this is just a constant with respect to time. Okay, this is a constant. This is a constant. These are constants. The only thing in any of this, everything to the right of this d by dt that's changing in time, is this I. That's it. Everything else can come out. So I'm going to have a mu naught L over 2 pi r, integral of R1, R2, dr over R. And that's just a number once I'm done with that. Okay. And I just have di wire dt. That's the only thing being acted on by the time derivative. Okay, so most of these things I know. Okay, I know the length of the wire. I know the resistance in the wire. The rest are constants here. This I know. This is just a number. That's 100 amps. So even though it's some funky derivative, it's just a number. It's a rate of change. Okay, that's just a number. So the last thing is just to do the calculus and evaluate this integral. And so we have mu naught L over 2 pi r. Since that's just a number, I'm going to put it right here. And I'm left with the integral of 1 over R, which is natural log of R. So it's the natural log of R evaluated at its endpoints, which finally gives us a mu naught L over 2 pi R, stuff we know, times the time rate of change of current in the wire, which we know, and then that's times the natural log of R2 minus the natural log of R1. Let's shift this over a bit. Okay, and these are all I know these dimensions. I've got them all labeled here, and I'll just assume I know them. Okay, and so I can plug in numbers here and get an answer. But the most important thing is, how do you play around with these two types of changes? Change in time and a change in space. And you just have to recognize what is changing and act only on that part, as we did in this example.